Which of these graphs show y as a function of x? Which one? Bottom left. Why? Because it passes the vertical line test. Okay, the other three do not pass a vertical line test. Which one of these is the red graph, the inverse of the blue graph? Oh, you know what's interesting is the images showed in a different order in my other class, and it was bottom left again. But it is the bottom right this time. How do we know if to find the graph and its inverse? What's their relationship? Yeah, they're reflected over y equals x. So if we look at the one in the top right, that one is a reflection of what? In the y-axis. The bottom left is a reflection in the x-axis. This one is, I don't know, some like a reflection and then a transformation. But this one is the red graph is the inverse of the blue graph. It's a reflection in line y equals x. Okay, this is fun. Some animation to show you reflecting in the line y equals x. And this is even more fun. Talk to me about the blue graph.
That's the sine curve.
It is the sine function. What do you think the red graph is? The inverse sine function. But is the red graph a function?
No.
No, it fails the vertical line test. I'm real excited. So this one, I didn't quite get how this works, but this was kind of fun to play with earlier because it sort of draws them and then there. Right. Don't lean back in my chairs that way. Isn't that weird? I don't quite get what it's doing, but it's fun to watch. It looks like they're chasing each other, doesn't it? Yeah. Okay. So that was that. And then I think that's all I wanted to do from this little demonstration. So let's go to the notes. All right, so that was a little demonstration. So we're doing 4.7, inverse trig functions. So just to remind you about inverses, we just talked about this a minute ago. They must be 1-to-1. So that means they must pass the horizontal line test in order for them to have an inverse function, because that means that the inverse would pass the vertical line test. The domain and the range switch, and the graphs are reflections in the line y equals x. All right, so you have some of these images on your notes in front of you. So this is the whole sine function curve here. So that entire sine function, does it pass the horizontal line test? No, it's not 1-to-1 if we look at the entire domain of the sine curve. So if we choose to restrict the function between negative pi over 2 and positive pi over 2, so that's what this little darkened bold section represents. That's negative pi over 2 on the x and this positive pi over 2 on the right. If we restrict it to just that section, then we see that the graph is increasing. We see that the sine graph takes on a full range of values, all the way from -1 up to +1. Because remember, the range of your mother function sine curve is from -1 to 1. So you got all the possible values there. And it's 1-to-1, which means we could take that little sliver there and we could reflect it in the line y equals x and get the graph of the inverse. So before we look at that, do you remember when we were doing like some inverse stuff in the calculator, and I said your calculator is always going to return an angle like in quadrant 4 for inverse sine and inverse tangent, and I said you would learn why later. Now it's later. Look over in the unit circle over there on the wall. And we restricted this function to be from negative pi over 2 to positive pi over 2. Negative pi over 2 is down there at the bottom of the circle, and positive pi over 2 is at the top of the circle. So your function is basically, it's like if you pivot up to pi over 2 and down to negative pi over 2, you're going to get a full range of values for sine. So in quadrant 1, all of the sine values are positive. And in quadrant 2, all of your sine values are negative. And the fastest way to get there would be to move clockwise to get down there, right? And so that is directly related to the graph of the inverse sine function. Like, it wouldn't make any sense to restrict, let me zoom in a little bit, It wouldn't make any sense to restrict the sine curve to be between 0 and pi, because then you wouldn't have any of the negative values. You could, if you wanted, I suppose, restrict it from pi over 2 to 3 pi over 2. You would get all of your values there, but we tend to want to center around the origin as much as we can. Okay, so when we take that little sliver and reflect it in the line y equals x, we get this. It's not very exciting. I don't really like to look at it much. It reminds me of a worm. You'll notice we've got some new notation here, the word arc. This is basically the same thing as this is the inverse sine function. You can either call it the arc sine of x, or you can call it the inverse sine of x. These are equivalent expressions. I want to write that down. Yeah, now you see why we have different notation now. Because this -1 does not mean 1 over the sine of x.
Okay, because
Okay.
that would be cosecant.
Yes, because that is equal to cosecant. It's the same thing that when we do this, when we did it last semester, this does not mean 1 over f of x. So it does get confusing with the notation of using a -1. It's not really an exponent. It means inverse in this situation.
Okay.
But that's a great question. I'm going to keep that in the video and give you credit, Will Hanson. Okay. I did want to mention as well, we're about to graph it by hand, which might seem a little bit silly because I'm showing what it looks like. But you'll notice also that the x-axis is labeled just going by like halves, like a half and 1 and 1 1/2 and 2. And now the y-axis is labeled with our fractions of pi. So if you wanted to graph this by hand, and we're going to do it right now, but you're not going to do it again, I just want to do it to sort of reinforce how you come up with the graph of the inverse sine function. So, if we were going to do just the graph of the regular sine function, I could just pick values of whatever I want for x. And I'm always picking angles. So I could pick -pi/2, -pi/4, 0, pi/4. Don't write this down, just watch. Pi/2. And I go to my unit circle. Well, what's the sign of -pi/2? -1. What's the sign of -pi/4? It's -√2/2. Sign of 0 is 0. Sign of pi/4 is +√2/2. And then this would be +1. So remember, if I wanted the inverse, and we did this last semester, if I want the inverse, I can just switch these columns. So that's what I have over here. The columns are just switched. So if I want to graph this by hand, I can label my x-axis. I need to go just from -1 to 1. So, you can just eyeball where you want -1 and where you want 1. And then for my y-axis, I want to go all the way up to pi/2 and down to -pi/2. So we can go by like quarters of pi. And -√2/2, do you remember what that decimal was? Yeah, it was -0.707. So you just kind of eyeball where -0.7 would be and then go down to -pi/4. We're not going to put arrows on the end of it because we are only looking at, if we start putting arrows on the end of it, the graph would actually continue and it would turn back and it would no longer be a function. All right, our inverse cosine function, very similar situation. It's not 1 to 1 when we look at the entire domain of the cosine function. So we're going to restrict the domain to just this interval from 0 to pi because we're going to get a full range of values from -1 to +1. And again, if you look over on the unit circle, in quadrant 1, all of your cosine values are positive. In quadrant 2, all of your cosine values are negative. So it's very convenient just to go quadrant 1 and quadrant 2 and we got all the same cosine values. We don't need quadrant 3 and quadrant 4 because all of those values are just repeated. And then if you were to take this little sliver and reflect it in the line y equals x, then you're going to get this little sliver. Also, this looks like a worm. The inverse tangent function looks pretty different because the tangent function itself looks pretty different. So what we do here is, so it's like with the sine curve, we're going to restrict it to be just this branch between these two asymptotes, between -pi/2 and pi/2, and reflect that one branch in the line y equals x, and then we get this graph. And of course, there's no arrows on it, but there could be arrows because it does go on forever to the left and to the right. So what's important about the inverse trig functions, and we're only doing the inverse sine, cosine, tangent, is their domains and ranges. Let's talk about the ranges first. So here's the arc tangent. What's the range of that function? -pi/2 to +pi/2. So negative pi over 2, sorry, we're down here, negative pi over 2. You can do the interval notation if you want. I'm going to use inequality notation. Notice that we're not equal to because you have an asymptote there. So negative pi over 2 to positive pi over 2. Let's look at the inverse sine function. What's the range on the inverse sine function? Yeah, negative pi over 2 and positive pi over 2, but this time we include those, so it's less than or equal to. If you were doing interval notation, you would need to use brackets. Inverse cosine function, what's the range? 0 to pi, inclusive. All right, let's do the domain. So for our inverse sine function, what's the domain? Negative 1 to 1. And the inverse cosine function, domain? Negative 1 to 1. And if you recall, the mother functions for sine and cosine, that was their range, right? So we're looking at, but for the tangent, domain, all real numbers, negative infinity to positive infinity. I'm not going to ask you to graph the inverse trig functions. It's useful to have an idea of what the graphs look like. And then it's also useful to understand their domains and their ranges. You can, we're not going to, but you can also transform the graphs, inverse trig graphs, the way that we do with any function. So this graph right here has actually been like a horizontal shrink there. So just fun fact. So one of the reasons that we restrict the range of the inverse trig function is so that we only get one answer to expressions like this. So let's look here at number 2. And it says, if possible, find the exact value. Now, when we graph trig functions, I'm going to use a theta instead of an x, but it doesn't matter. What goes inside the trig function is usually an angle, right? Well, not usually, it's always an angle. And then what comes out is we call it a value. That would be the sine of pi over 6 or whatever. Now we're going backwards. So what's going to come out of that, we could call that theta. I want to know the angle whose sine is negative 1/2. So looking at the unit circle, what angle has a sine of negative 1/2? Negative 30 degrees. Is there not another one?
330.
Yeah, you could say 330,
210.
210. But remember, the arc sine domain is restricted. You can only give an answer that's between negative pi over 2 and positive pi over 2. Or negative 90 to positive 90 if we're doing degrees. So you have to give negative 30 degrees, or if you were answering in radians, usually it'll specify if you want degrees or radians, negative pi over 6. So whenever you see this notation, an arc cosine of some value, this really means find the angle whose cosine is equal to that. So we're answering in angles instead of giving angles and finding the value. What do you think about number 3? Because the arc sine function doesn't go any further than 1. Also, if you think about it, we're saying what angle has a sine of 1? Or if you're looking at the graph of sine, sine of 2, you're never going to get up to 2. It peaks at 1. Right? Because the range of the mother function is from negative 1 to 1, so you're never going to get to 2. So it's not possible. This is why students will come to me all the time and they'll say, my calculator's broken. I tried to do the inverse sine of 2. It doesn't matter what mode you're in. You're going to get an error. Try numbers 4, 5, and 6 on your own. 4, 5, and 6. Use a calculator. Yeah, negative 83 point something, right? I'm sophisticated, so I have it in degrees and minutes. Negative 83 degrees and 15 minutes or something like that. If you were in degrees. Or if you were in radians, what'd you get? Yeah, negative 1.453 approximately. It didn't specify which to return the answer in degrees or radians, so I'm giving you both. What about number 5? Not possible. For the same reason that number 3 was not possible. The sine and the cosine, you cannot return an angle if the value is never bigger than 1. Okay, so you try it, your calculator would give you an error. What about number 6? This one's tricky to try to figure out how to type it in. Yeah, okay. So let's think about this. If I were to set this equal to theta, because an inverse or an arc secant would always return an angle, then this means that secant of some angle is going to equal 3.4. Well, I don't have a secant button on my calculator, but secant is the reciprocal of cosine. So if the secant is 3.4, then the cosine of the angle would have to be 1 over 3.4. So in your calculator, you need to do the inverse cosine of 1 over 3.4. Yes, 1.272 I have. So 1.272. If you're in radian mode, if you're in degrees, you'd get something different. What you have to be careful with is this is not 1 over the inverse cosine of 3.4. You're not doing the reciprocal of the entire inverse function. It's the reciprocal of the value, right? So think about SOHCAHTOA, that's adjacent over hypotenuse, that's the value. So we'll have to do a hypotenuse over adjacent for this. Okay, composition of functions. You recall we did this last semester. F of f inverse of x usually equals x, and f inverse of f of x is equal to x. So it seems like we can do the same thing with the trig, that you can just sort of cross those out and call that 30 degrees. Sometimes you can, but sometimes you can't. So the approach here is to work from the inside out. So looking on the unit circle, where is the cosine 30 degrees? I'm sorry, what is the value of cosine of 30 degrees? Root 3 over 2. So I'm just going to replace the cosine of 30 degrees with root 3 over 2. So now we're looking at the inverse cosine of root 3 over 2. So now let's work with this. It's saying, what angle has a cosine of root 3 over 2? 30 degrees. So in that case, we could have just crossed those out and just said 30 degrees. And if they give you an angle in degrees, you need to answer in degrees. If they give you something in radians, you need to answer in radians. Okay, let's do the next one. Cosine of the inverse cosine of root 3 over 2. So the inside part is saying, where is there an angle whose cosine is root 3 over 2? 30 degrees. So now we replace that. We say cosine of 30 degrees. And what's the cosine of 30 degrees? Root 3 over 2. Again, it seems like I could have just crossed those out and just given the root 3 over 2 as an answer. Caution, cosine of 210 degrees. Negative root 3 over 2. So if I replace that, now I'm looking at the inverse cosine of negative root 3 over 2. Now this is asking, which angle has a cosine of negative root 3 over 2? 150 or 210, but we have to give an answer that's in quadrants 1 or 2 for the inverse cosine. So it has to be 150 degrees. So that's a situation where you cannot just cross that out and give 210 degrees. This is not equal to 210 degrees. I mean, one clue, and this is, you can't always interpret it this way because it's not always written this way, but 210 degrees is outside of the domain of the inverse cosine. So you can't answer 210. You can only answer between 0 and 180 for cosine, and between negative 90 and 90 for sine and tangent. Let's do one more. Let's see if you can do this one on your own before we get to example 7. All right, try this one. The arc sine of the sine of 3 pi over 2. Okay, this is a radian measurement, so you need to answer in radians. So let's work from the inside out. So cover up the outside and figure what is the sine of 3 pi over 2? It's negative 1. So replace that bit with negative 1. So now we're looking at the arc sine of negative 1. So this is now saying, where is there an angle between negative pi over 2 and pi over 2 whose sine is negative 1?
Negative pi.
Negative pi. It's a new dance move. Y'all start doing that at your parties. You shouldn't be having parties because there's this pandemic.
No
but
parties, guys.
Try numbers 7 and 8. All right, what'd you get for number 7? Negative pi over 3. So again, working from the inside out, sine of 5 pi over 3, that's down there in quadrant 4, and the sine is negative root 3 over 2. You can't use 5 pi over 3 because for arc sine, you have to return an answer that's between negative pi over 2 and pi over 2. Then we say, now, where's there an angle between negative pi over 2, pi over 2, and that is at negative pi over 3. Right? What about number 8? It is negative 5. Now, for that one, we've never seen anything like the tangent of negative 5. Now, remember, if you tried to type, if that were anything other than tangent, like sine or cosine, you would get an error because you can't go down to negative 5 on sine and cosine. But for tangent, you can, because remember, the inverse tangent curve, the domain is all real numbers, because the mother function tangent curve, the range is all real numbers. So you can just, it doesn't matter what mode you're in, if you were to do the tangent of the inverse tangent of negative 5, you get negative 5. And it'll make more sense if you do it in degrees. I'm in degree mode. You could do this as well. Check this out. So 5 pi over 3 in degrees is 300. So if I did second sine of sine of 300 degrees, negative 60. Let's talk about numbers 9 and 10 are very similar to each other. Obviously, this is 2/3 is not something that we've seen on the unit circle, so we're going to use a technique that we were using a couple of weeks ago. We're going to draw a triangle. So we want to say if this whole thing, if we let that equal to theta, then essentially we have like theta is equal to the arc cosine of 2/3, which really means the cosine of some angle is 2/3. So let's draw a triangle and label it so that the cosine would be 2/3. It's positive 2/3, so we can be in quadrant 1. How can we label the triangle so the cosine would be 2/3? Hypotenuse is 3, adjacent is 2, finally the other leg. It is the square root of 5. Remember, that would be your theta right there by the origin. So now that we've labeled the triangle, we really are trying to find the tangent of theta. So we can just go SOHCAHTOA to our triangle, root 5 over 2. Well, the answer is just the root 5 over 2 part. Now, you can check that in your calculator. I would not recommend that you just use your calculator for the test because it does say exact value, and your calculator will not give you that. But if I were to, I'm going to do it in degrees so you can kind of see how it's thinking. If I do the inside, I do the second cosine of 2/3, then your calculator returns this 48-degree angle. So then they want to know, well, what is the tangent of 48 point whatever. So you can do tangent of that angle, and you get that decimal. When I did it by hand, I got root 5 over 2. So let's see, what is root 5 divided by 2? The same thing, therefore I'm right. Let's take a look at the number 10. So similar thing, except this time we have this 3x, where here we just had a fraction of 2/3. Now don't worry about this restriction on x, where x has to be between 0 and 1/3. It just means because we know that for arc cosine, you can't have a value that's bigger than 1 or smaller than -1. So let's do the same thing. We can let this inside bit equal to theta. So we have theta is equal to the arc cosine of 3x, or in other words, cosine of theta is 3x. It's positive, so we can go again in quadrant 1. We want to label the triangle so that the cosine of theta would be 3x. Yes, make the hypotenuse 1, 3x the adjacent side. Find the length of the other leg. Can I just call that 1 minus 3x?
Yeah.
No. Because these, you can't take the square root of separate terms like that. There's no such thing as doing like a square root of a squared plus b squared. That is not equal to a plus b. The square root of a squared times b squared is equal to a times b. And if you had the square root of a plus b, the whole quantity squared, that is equal to a plus b. But if you have individual terms that are squared, you cannot just take the square root separate like that. So the b is the square root of 1 minus 9x squared. And what we really want here is the cotangent of theta. And you do not need to rationalize. You can leave it like that.